Good evening, everyone. I really would like to be there with you in Whitehorse, but it's a bit of a commute from upstate New York, so we're going to do the best we can with modern technology. I want to thank all of you who are in the audience and also those of you who are viewing this through live streaming. It's a great honor, and I think it's a privilege for me to be addressing you tonight, and I'm looking forward not only to speaking to you, but to hearing from you during hopefully what will be an also very informative question and answer session when I'm done with this formal presentation. So let me begin by telling you what we're going to do, and then we'll do it. So the first thing I'm going to do is answer some of the questions that you have sent to me. With the various communications I've had with the organizers of this session, I received a long list of questions, and it turns out that I had already intended to address some of them, so it's perfectly timely, and it's obvious to me that many of you have done your homework. So I'm going to begin by answering some of those questions up front, but I'll answer all of them during the talk that I'm going to give you. Then I'm going to go into what is new for oil and gas in the Yukon. There has been oil and gas development in the Yukon in the past. Why is there a concern now? Why is there more concern now? And then I'm going to give significant details on what it takes to get gas and oil out of shale, because that is what's new. How to get gas and oil out of shale. Fracking is one part of it, but it's not everything. Then I'm going to spend some time talking about what can and does go wrong during this process of getting oil and gas out of shale. I'll concentrate on two specific things in that area. And finally, I want to summarize what the science, the peer-reviewed, highly vetted, prestigious science says about the negative impacts on water, on air, and on human health due to the development of shale gas and oil. So that's what we're going to do over the next 8 or 9 hours. It's okay that we start at 9:30 at night. You people are still having early evening. I can go forever. So here's the list of some of the questions you sent, and I'm going to begin by addressing the first two. So I'll read the questions, and I'll give you my answers. So I've been told by you that there's been some misleading information about conventional versus unconventional development. Some people are saying they're the same thing. So you want me to explain the difference, and I will. And by the way, I'm not at all surprised that there's misleading information. Welcome to the club. And related to that question is a second one, which is it true that fracking, which is also called well injection, which is also called hydraulic fracture stimulation, is it true that it only happens in conventional wells or only happens in unconventional wells? So let's address those two questions first, and they will be a lead-in to my answering some of the other questions and other things I wanted to talk to you about tonight. So, formal definition. If you were to go to the Oil and Gas Industry Bible, it's put out by a company called Schlumberger. It's called the Oil and Gas Field Glossary. Any definition of any term that you would ever want to get in the oil and gas field, you can go on the website, there's the URL, and get it exactly from the horse's mouth. So how does one define today what is unconventional as opposed to conventional? And this is word for word the definition, and I've highlighted the key words. At present, the term unconventional is used in reference to oil and gas resources whose porosity, permeability, and fluid trapping mechanism differ from conventional sandstone and carbonate reservoirs. Let me translate that. Conventional oil and gas comes from sandstone or carbonate reservoirs where it has been trapped. Carbonate reservoirs, sandstone reservoirs do not create oil and gas, they trap it. On the other hand, what's currently called unconventional means it's either coal bed methane, gas hydrates, shale gas, fractured reservoirs, and tight gas sands. So since we're talking tonight about shale gas, and since you can only get gas out of shale if its reservoir is fractured, We are talking about unconventional oil and gas development. So let me repeat. Conventional means that the oil and gas has migrated from someplace else and has become trapped in a sandstone or carbonate reservoir. When we're talking about shale, shale is the source of oil and gas. It's where it comes from. It has not migrated out of the shale. It's still there. And when you develop an unconventional oil or gas well in shale, you're trying to get the gas and oil from its original source. I hope that's clear. If it isn't, you can ask me questions later. So related to this issue of conventional versus unconventional, and this is very confusing, so I'm going to try to unconfuse you, is the issue of fracking. So the question I got was, is it true that hydraulic fracture stimulation, also called well injection, also called fracking, only happens in conventional wells? No. No. Fracking can and does occur in both conventional wells and in unconventional wells. The difference is, for you in the Yukon concerned about shale, that it is possible to get oil and gas out of a conventional well without fracking. Even though most conventional wells today are fracked, it is sometimes possible to get oil and gas out of a conventional well without fracking. But it is impossible to get any economically viable volume of oil or gas out of shale without fracking, which is another way of saying all shale gas and oil wells must be fracked. In fact, they must be super fracked. And I'll get to that difference between fracking and super fracking in a few minutes. So again, I hope I've answered that question. Next question. Could I please explain what a perfing gun is and how it is used? Perfing. Well, first of all, perfing is an abbreviation for perforating, as in take a piece of paper and punch your finger through it, or punch a pencil through it. You're perforating the paper. Except in oil and gas, we're not perforating paper. So the purpose of perforating is to burn holes in what's called the well liner, also called casing. It's steel pipe. As you'll see in a few slides when I actually blow up a well and show you what's inside of it. And very important part of the structure of an oil or gas well is layers, concentric layers of steel pipe called casing. Well, you can't get gas or oil to come into steel casing unless you put holes in it. And you can't fracture the rock, you can't put fracking fluid out into the shale without having holes in the casing. So the purpose of a perforating gun is to, quote, shoot, although it really doesn't shoot a solid, it shoots a very, very high temperature liquid into the casing, burns through the casing, and burns a hole into the rock. The whole idea is to give access for fracking fluid to go out of the casing and for oil and gas to flow back in. So what are these perforating things? They're not really, the word gun is, one thinks about bullets, but there's no bullets here. You're not shooting a solid. They're shooting a very high velocity jet of liquid copper. So I'm not going to go through the details on this slide. You can go to the website, the Oil Field Review by Schlumberger. It will give you all kinds of details. They're basically shaped charges. Those of you who have been in the military or have followed the military or read about military books, shaped charges are used, for example, to penetrate armor in the military. Not with a solid, but with a high velocity, high temperature liquid metal, in this case copper. So that's what perfing is done. That's a perfing gun. That's what is necessary during the fracturing process. Thousands of holes need to be burned through the casing in a typical shale gas well. So thousands of these shaped charges have to be created, transported, stored, dropped down into the well, placed exactly so that they get the holes in the right place, in the right orientation. So let me show you, by taking apart a well, all these components that I've been mentioning, like casing and perforating and cementing. So this is an experiment I was involved in some years ago. You can see the date on it, July 1989. I had black hair back then, and my kids were still kids. We did laboratory testing down in Utah on large blocks of sandstone. So this is a conventional rock. This is a rock that would have absorbed gas or oil from shale. And we purposely did these experiments to try to understand the process of hydraulic fracturing. So this is a cube of sandstone, roughly 2 meters on a side, and we drilled it, we put casing in it, we cemented the casing, we put a perfing gun in it, we perforated the casing, we injected hydraulic fracturing fluid, and we fracked it. So this is what we found when we broke open that block. I'm going to break that block in half and show you what's inside. So on your left, you'll see this silver casing, that's the steel pipe. You'll see that it's surrounded by a gray layer, and that's cement. The same kind of cement you would get by going to your local hardware store and buying a sack of cement, mixing it with water. It's not concrete, it's cement powder mixed with water and other chemicals. And here you can see perforations. There's a hole here that went through the casing and into the rock. There's a hole in the casing here that went into the rock. Here you can see a hole that went through the casing in the cement. Here you can see a tip of a perforation out in the rock. In this red area is a hydraulic fracture. We put red dye in the fracturing fluid so that we could see the actual hydraulic fracture shape and propagation. So there's the basic elements of a gas or oil well: casing, cement, perforations, rock. Next question I'm going to answer right up front. To my knowledge, does fracking cause earthquakes? Yup, yes, definitely, for sure. In 2 ways: indirectly and directly. By indirectly, I mean that when a well is fracked, and a typical shale gas well in British Columbia is fracked with 40 or 50 million gallons, I should say liters, 40 or 50 million liters of fracking fluid. Much of that fluid comes back up the well after the fracking process, and that's called flowback. So that's a waste. It's no longer drinking water. It's now wastewater. It's contaminated. So it has to be captured, it has to be stored, it has to be transported, and it has to be put someplace safe forever. In the United States, in most cases, it's re-injected back underground in a waste disposal well. A waste disposal well is typically an old oil or gas well that is no longer producing oil or gas. So it's now capable of receiving large volumes of waste fluid. The problem is that this process has been overdone. Overdone in places like Oklahoma, Texas, Arkansas, Ohio, and England, among others. And in the process of injecting down underground, deep underground, large volumes of this waste fluid at high pressure, faults, naturally occurring faults in the earth, have been mobilized. So hold your hands together. I can't see you, but take your hands and put them together as if you're going to clap. All right? So between your hands is a fault. That's a crack. It's a natural crack. Now, slide your hands relative to each other. You just made an earthquake. Now, when you inject fluid underground and that fluid gets into that fault, your hands become slippery and they slide easier. And if you inject the fluid under too high a pressure, you basically take the pressure off of your hands so that they're barely touching, and now they're easier to slide. There you go. Human-made earthquakes in 15 seconds using your hands. So how often has this happened? Well, in Oklahoma, I'm showing you a plot here that says in 2000 there was exactly one earthquake of magnitude 3 or greater. In 2015, there were 680. Notice starting in 2009, the drastic increase in earthquake activity in a place where there had never been any significant earthquake activity. It just so happens that that's the period of time in which shale gas and superfracking came into play in the United States, not only in Oklahoma, but a number of other states. So much so that now the United States Geological Survey, which issues maps of earthquake intensity and earthquake risk, now shows that the area in Oklahoma and Kansas and Arkansas and Texas, where there has been a large amount of shale gas and oil fracking and waste disposal, has very high risk of earthquakes. We've now made Oklahoma as risky as San Francisco. Thank you, oil and gas. I'm sure the people of Oklahoma really appreciate what you've done for them. Second way that earthquakes can happen is directly by fracking. Fracking itself is, by definition, fracturing. Fracturing, by definition, is an earthquake. So, there have been many instances of fracking directly causing earthquakes, most notably not too far south of you in the Horn River area of British Columbia. So in December of last year, there was a 4.6 magnitude earthquake. At that point, the largest man-made earthquake ever recorded. I said the largest man-made earthquake ever recorded from oil and gas operations. Not quite a year ago. And I then found out that that wasn't the world's largest because in January of this year in Alberta, a 4.8 occurred. So 4.6s and 4.8s are not going to shake buildings to the ground, but they are going to crack walls. They're going to induce settlement. They're going to knock things off of shelves, and they could injure people. The question now that the earthquake scientists are considering, and this is a very important problem, and they're very worried, what's the upper end? How large an earthquake can be caused either indirectly or directly? What we've seen over the last 7 or 8 years is that the magnitudes keep increasing. 7 or 8 years ago, the oil and gas industry was absolutely certain that they had never caused an earthquake. Never. In Texas, they still say that they don't cause earthquakes, but that's Texas. They're a different country. But all of the scientists, all the prestigious, real, honest-to-goodness scientists in the earthquake area are absolutely convinced that oil and gas operations now cause earthquakes with increasing frequency and with increasing maximum magnitude. And we are at risk in the U.S., and you are at risk in British Columbia, of having a significant earthquake, a 5.5, a 5.6. Okay, a 5.6 is 10 times stronger than a 4.6. Buildings will collapse. There are 2 other questions I'm going to address, but I'm not going to do them right now. They will be addressed later as my talk develops. I'm going to talk about climate change, and I'm going to talk about the downsides of hydraulic fracture stimulation and the downsides of waste from hydraulic fracturing. So I will answer those last 2 questions, and you'll hear the answers later on in my talk. So let's proceed now back to my outline. The first thing I wanted to do is answer the questions you sent me so we get all the definitions and all the incorrect notions and misinformation out of your minds. Now you have it from, quote, the horse's mouth. Everything I just said is correct and true. And by the way, I hope that there are oil and gas representatives listening to this presentation somewhere. And if you hear me say something that you think is incorrect, please contact me directly and we will discuss it. I don't want you doing what they do in the U.S., which is you go on your stupid blogs and you criticize my talk without my opportunity to engage with you. Be professional. If you think I'm saying something incorrect, tell me to my face. So, what is new for oil and gas in Yukon? I already told you. What's new is shale. Now, how do you get oil and gas out of shale? I'm going to use a bunch of pictures and videos and graphs and charts taken directly from the oil and gas industry. You'll see that this chart that I'm showing you right now was created by Chesapeake and Statoil, two major companies, trying to explain to their shareholders the process of getting oil and gas out of shale. So I'm going to spend a minute or two explaining it to you because this is really important. This is unconventional development of oil and gas from shale in one picture. So here's the surface of the earth. Down here, this gray box is a layer of shale. Shale occurs in layers over very, very large expanses, many hundreds of kilometers in every direction. So here's all your shale. Here's the surface. On the surface in this picture, there are 4 pads. A pad is a place where the drilling occurs. I'll show you pictures of pads. But here's a pad, here's a pad, here's a pad, and here's a pad. Now, to get oil and gas out of shale, you can't just drill directly vertically down. That's what you would do in sandstone or a carbonate reservoir because the oil and gas would be trapped in a pool directly below your wellhead. But in shale, the gas and oil is distributed. It's everywhere in the shale. So since the oil and gas is everywhere in the shale, you have to drill everywhere in the shale. So in each pad here, there's not 1 well, but 6 wells. And they start off coming down vertically, and then they deviate. This is called deviated drilling. So nowadays they can drill well in any direction they want. So they start off vertical, then they curve, and they go more or less horizontal so that the well is along the shale, not through or into the shale. So this is called the lateral. And all these little fuzzy spaces here are supposed to be fracking. So we frack the shale here, we frack the shale here, frack the shale here, and you'll notice that these laterals can be over 2 kilometers long. But they're only about 150 meters apart because the idea is to try to drain as much oil or gas as possible out of this volume of shale. You'll notice the distances here. So on the surface, in one direction, the pads are only about 1.5 kilometers apart. In the other direction, they're about 3 kilometers apart. This yellow box is meant to indicate all of the surface area that this particular pad would account for. It's called a development unit or a spacing unit. So a company gets a permit to put a pad, put 6, 8, 10 wells on that pad, and try to get all the oil or gas beneath that yellow square. And I'll show you what those yellow squares do in a few minutes. But what this picture captures is the essence of unconventional development of oil and gas from shale. It is the only way that has been developed, and I predict the only way that will ever be developed to get, hopefully, economically viable volumes of oil or gas out of a shale formation. And what you're seeing is what's called clustered multi-well pads with high volume long laterals. It's not called fracking in my terminology. That's too short a word. You got to use all the right words. Clustered means, look, 1, 2, 3, 4, and there would be more over here and more over here and more over here. Multi-well, every pad has many wells. 6, 8, 10, 12, 20 wells. High volume. I mentioned 20 to 50 million liters of fluid being injected into each of these wells. Long laterals, 2 kilometers or more. So, having done all that, the problem is that this whole process is very inefficient. Industry isn't going to tell you that. You should ask, what percentage of the gas owned by the province, what percentage of the gas in the shale formation are you actually going to produce? Or what percentage of the oil are you going to produce? And they should be honest and tell you, well, we're probably at best going to get 10% of the gas and about maybe 3 or 4% of the oil. So all that effort, tens of millions of dollars on each well, all that fracking, all that heavy equipment, all the infrastructure that we're going to see, all the pipelines, all the compressor stations, all the processing units, all the truck traffic, all the new roads, all the new pipelines, and they're only getting a very small fraction of what's there. Why? Because shale is stingy. Shale is mean-spirited. Shale is getting even with humans. I'm lecturing here from my pulpit. Shale is getting even with humans because it's angry that it was the last kind of rock that the oil and gas industry went to. It's been lonely for 150 years. It's been waiting for the oil and gas industry to come and take it. And because it waited, it's like the poor guy who was hoping that the most beautiful girl at the dance was going to come and ask him to dance, but she never came over, and now he's really upset. So I'm joking here, but the point is that it's very, very difficult to get oil or gas out of shale. That's one of the reasons the oil and gas industry waited until the end of the fossil fuel era. It's very expensive, it's very difficult, and yet it's still very inefficient. So the best they can do is to use two approaches: spatial intensity and technologies of scale. By spatially intense, I mean you have to have a hell of a lot of pads with a hell of a lot of wells in any one area. As I just showed you, you have to drill everywhere. Drill as many wells as you possibly can in any one area to try to get as much oil or gas out of it as you can. Technologies of scale means that compared to conventional wells, where the oil and gas had accumulated in one place, everything is bigger. Everything is bigger with shale. And I'll list all the things, and I'll tell you about how much bigger they are in a few minutes. So what do I mean by spatially intense? If you were flying over Texas in the area around Dallas and Fort Worth, Dallas and Fort Worth are a few kilometers off to your right in this map. Here's your scale. This is 4 kilometers. Every one of these white dots is a pad. I repeat, every one of these white dots is a pad. And every one of these pads has many wells. So there have been 15,000, actually more now, there are 18,000 wells drilled in the Barnett shale play, just to the west and north of Dallas-Fort Worth. I'm going to blow this up so you get a better view. So now I've gone to a 1 kilometer scale, and again, each of these white dots is a pad. And as you can see, more or less 1 or 2 kilometers between each of the pads. So now I'm going to ask you to use your imagination. If there's going to be shale gas or oil development in the Yukon, is it going to look like this? Must it look like this? Is there some other way to do it? It will look like this. There is no other way to do it. So let's transport ourselves into the future. Hopefully a not true future. But let's go to the Yukon. And let's go to some area south of where you're sitting. Here's Whitehorse. We're going to get down here near Carcross. And this is an area that's been designated as an unconventional resource. Here are shales. So let's go into this red box. So this is the area inside that red box. Here's Carcross, Route 2. Now remember that yellow square I showed you around the pad on that image I showed 3 or 4 minutes ago? Let's start putting pads in this area at the same spacing that I told you must be used, that the industry would like to use for clustered multi-well pad development. Bingo. Every one of these yellow rectangles is a spacing unit or development unit for a pad. Each one of these red dots is a pad. And the idea is you don't leave any stone unturned, pardon the pun. You want to drill everywhere. If there's gas or oil everywhere in the shale here, you want to drill everywhere. And so from each of these pads, there would be 4, 6, 8, 10, 12 wells. Depends upon the geology and how much money they have. Now, as you heard a few minutes ago, the previous speaker mentioned that these wells deplete very quickly. A shale gas or oil well runs out of gas, pardon the pun, in 4 or 5 years. After 4 or 5 years, it's a stripper oil well or a defunct gas well. Turn it off. It's not worth maintaining. So a company will come in and drill the first 2 or 3 wells from this pad, and then go off and drill 2 or 3 wells from this pad, and then 2 or 3 wells from this pad, 2 or 3 from here, 2 or 3 from here, and then come back 2 or 3 years later and do 2 more here, 2 more here, 2 more here. In other words, they're going to be around a long time drilling. Years. That's another difference between conventional and unconventional. A conventional well, you drill, you move away. There's only one well. In unconventional, you're back again and again and again. Technologies of scale. So I told you everything is bigger compared to conventional. You need the largest drill rigs in existence. They're called triples, with very large horsepower diesel engines driving the drilling motor. You need much larger fracking equipment. You're fracking at pressures that are 3 or 4 times higher than conventional wells. You're using 100 times more fracking fluid than a conventional well. And you're using 10 times the horsepower for the pumps. Typically 15 to 20,000 horsepower necessary in a frac job. Because you're using so much fracking fluid, you get a much higher volume of waste fluid called flowback. You're going to have larger and longer flaring and venting. And by the way, I have read your regulations for Yukon, and frankly, they are wanting. They do allow flaring and venting. Venting is direct emission of methane into the atmosphere during flowback. I'll show you a picture of flaring in a few minutes. A lot more truck traffic because you have to transport large volumes of water and large volumes of fracking fluids and large volumes of sand and a hell of a lot of equipment to each pad multiple times. Not just once, multiple times, because they're not going to do all 8 wells in a pad at the same time. You got to connect every well with a pipeline. If it's a gas well, the only way to get the gas out of the well is into a pipe. So you got to create pipelines. Every well has to be connected by pipeline to a compressor, to a dehumidifier, and if it's wet gas, to a processing unit. So you're going to need compressor stations. I'll show you pictures of what those look like and some of the bad things they do. So more and larger compressor stations compared to conventional, and more and larger processing plants if you have wet gas. And of course, much higher greenhouse gas emissions. And we'll spend time talking about that. So, what does a pad look like? I showed you an artist's rendition. This is the real thing. This is a photograph of one of the largest pads ever. It's in British Columbia, not far from where you're sitting. And in my opinion, British Columbia has always been the experimental playground for shale gas development, because there aren't too many people around. And you'll notice there's been a tremendous amount of tree removal, a large amount of earth moving. Here's your freshwater pit to store water for the fracking process going down, and here's your wastewater pits, take the flow back, coming back up. So all this waste has to go someplace. And you better be asking the people who want to drill in the Yukon, what are they going to do with it? Do you have injection wells in the Yukon? Has anybody checked to see if they're on fault systems? And if you don't have injection wells, where are you going to put all this stuff? So this is probably a 15 or 20 well pad. And when I say that the British Columbia has been a testing ground, this is British Columbia, this is Pennsylvania. Look familiar? Large amount of tree removal. And by the way, trees are called carbon capture and sequestration units. Talking about climate change here. This is called burning your candle at both ends. You're killing a large amount of trees, and the trees are there to absorb carbon dioxide, and you're producing a large amount of gas, which produces a large amount of carbon dioxide. Bad news at both ends. Flowback impoundment that you saw up in British Columbia, here's a flowback impoundment in Pennsylvania. Notice the close proximity to human habitation. This is toxic material, liquid and gas. Here's a flare. I hope you get the scale here. Flaring means you're burning off the gas that's coming up of the well, whether it's an oil well or a gas well, during the flowback period after fracking for a few days or a few weeks. They don't capture the gas, they vent it or they flare it. This flare is over 100 meters high. And I wish I could show you what the sound is that it makes, but it lights up the countryside. And it has the sound of a jet engine continuously for days. Very disruptive of sleep patterns, disturbing children and animal life. Compressor stations. When the gas comes out of the well, it might not be at a high enough pressure to enter a transmission pipeline. So the gas has to be increased in pressure with a compressor station. Inside these buildings are 2,000 horsepower pumps that are pumping up the pressure in the gas. As more and more wells are built, and as more and more pads are built, compressor stations become larger. So here's a more modern version of a compressor station. 1, 2, 3, 4, 5, 6, 12 buildings, each of which contains two 2,000 horsepower pumps. They make a lot of noise. They emit a lot of greenhouse gases. And sometimes they have accidents called blowdowns. So I'm going to show you a video. And Jason, if you can cue up the first video at this point. This video is what's called a blowdown event. There's an overpressurization in the compressor station, and an emergency valve kicks off, and a very large volume of methane, natural gas, is emitted into the atmosphere directly. Let me know when the video has started.
We're going to start it right now if it works.
Okay. Is it going? Good.
It's been going on for half an hour now.
So this program event in this particular case was in Pennsylvania, not far from where I live now, and it lasted for over an hour. And I hope you can hear that very loud noise it's making. It goes around the countryside. You can hear it from miles away. And literally thousands of cubic meters of methane are vented directly into the atmosphere. This is not uncommon. You have compressor stations built in your area, you should expect to see this happening. Okay, you can shut that one down, Jason. I mentioned processing plants. These are mini refineries. If it turns out that the natural gas that you have is wet, which means it's not just methane, it would have propane, butane, ethane, higher order, what are called alkanes, then all those different kinds of gases and liquids have to be separated. That's what's called processing. And these processing plants are also large industrial complexes. These are in West Virginia, Ohio, and Pennsylvania. So, bottom line, shale gas and oil requires a large number of multi-well clustered pads and what I call significant ancillary infrastructure. By ancillary infrastructure, I mean pipelines, compressor stations, processing units, dehumidification units, storage units. In other words, you take an area like south of Whitehorse and you take bucolic countryside, which is what it looks like from Google Earth, and you turn it into an industrial complex. If that's what you want, vote for it. Next topic, what can and does go wrong? I'm going to pick two things. Many other things I could talk about might come up during Q&A, but I'm going to pick two things. Drinking water contamination and methane emissions into the atmosphere. So we'll start with drinking water contamination. So what you're looking at now is a picture, a still image, of a wellhead. This is where the steel casing that I showed you before comes out of the ground at the surface, and there should be gas coming up the inside of this steel pipe and going into a pipeline. And I'm going to ask Jason to run this video, and what you're going to see is this pipe coming out of the ground going into a pipeline, but you're going to see that the gas is not only coming up inside the pipe, it's coming up outside the pipe. Go ahead and do that video. And let me know when it started. Thank you. So you'll see that there's been water collecting around the wellhead. That's probably snow melt or rainwater. And that bubbling you see is methane gas that's leaking outside the well, coming up into that water, and it looks like it's boiling the water, but it's just gas, like fizz in your fizzy soda drink. And that's methane going into the atmosphere. But it's also going through the groundwater table. So if the gas is leaking outside the well and it's getting to the surface, that means it had to go through the groundwater, which means the methane is now contaminating a drinking water supply. This is bad. And it happens too frequently. You can stop that video now, Jason. Thank you again. So how frequently does it happen? Depends upon how well the well is built. So these are videos created by another large gas company, Southwestern Energy, to show the good, the bad, and the ugly. So here's the wellhead, here's the casing, the gray is the cement, here's your shale formation, but usually when you have one shale formation, you have multiple shale formations, and you might want to be getting the gas out of this formation, the lowest one, but there's also gas in the other ones. And so if your well is correctly constructed, you have cement acting as a gasket so that the gas in this layer of shale can't get into the well. The cement is doing a good job. The gas is only coming out of the producing formation going to the surface. Bad things can happen. One of the bad things that happens all too frequently is the cement job is bad. And the cement job can be bad for many reasons, and the industry knows it. There are literally 5,000 publications that I'm aware of in the industry compendium talking about bad wells, leaking wells. So if the cement is not doing its job as a gasket, then gas from these intermediate formations can get outside of the casing that's supposed to be transporting the gas. And if the gas is not allowed to vent into the atmosphere, and it should, by your regulations, the gas is supposed to vent into the atmosphere, but if that vent is somehow blocked off or frozen, pressure builds up, the gas migrates into an underground source of drinking water, and your well water goes bad. You can have a casing failure, corrosion, cracking. Again, casing fails, gas leaks out of the casing, same thing can happen. The gas can get into an underground source of drinking water. Or maybe the cement didn't go where it was supposed to go. It's not like you can go down the well and look. There are techniques, technologies that can be used to investigate whether a well is well constructed or not. Some regulations require them, other regulations do not. You might not know until the well goes bad that it had a bad cement job. And then it's very expensive and sometimes impossible to fix the well. How often does this happen? We published a paper a few years ago looking at the frequency of occurrence of leaking wells in Pennsylvania. And what we found is that unconventional wells were failing at a rate of about 6.2%. 1 out of every 16 modern shale gas wells, modern, in a state which has very tough regulations, much tougher than the regulations in the Yukon, 1 out of 16 wells was failing within the first 3 years. And in some places in Pennsylvania, 1 out of 10 was failing in the first 3 years. That's a lot of leaking methane. And we'll talk about what that's done next. So back in 2011, I was privileged to be a co-author on a paper that caused some consternation, some controversy. We published a paper in which we said that shale gas, when compared to conventional gas or coal or oil, was the worst possible thing for climate. So I'm not going to try to explain the units here, but the taller these columns, the worse it is for climate. And this pink is methane, the blue is CO2 indirect, and the black is direct, meaning when you burn it, you get CO2. All those diesel engines burning diesel create CO2. So we said that shale gas was emitting into the atmosphere, unburned, somewhere between 3.6 and 7.9% of all the shale gas produced in the U.S. was never being burned. It was just getting into the atmosphere, leaking, venting. And that made shale gas the worst possible fossil fuel from a climate change perspective. And in 2011, we were pilloried. Even the White House criticized us. Said it can't be true, impossible. Fast forward. 3 years later, our White House publishes 2 major reports. Climate change impacts in the U.S., a whole chapter on methane emissions. And then an entire new plan, a climate action plan, strategy to reduce methane emissions. Oops, we were right. Every paper that's been published since 2012, in which people actually went out and measured methane emissions from oil and gas operations in the United States, has shown that that range that we predicted captures what's actually being measured. Okay, well, if this is true, if there is a lot of methane getting into the atmosphere, we should see it when we measure methane concentration in the atmosphere. And if you didn't know this, you're going to find out tonight. There is only one place on the face of the earth, one place, on an island in the Hawaiian chain out in the middle of the Pacific Ocean, where the United States government, in cooperation with governments all around the world, including the Canadian government, makes official measurements of the concentration of carbon dioxide in the atmosphere and methane in the atmosphere. And this is a record starting in 1960 of the concentration of carbon dioxide in the atmosphere. And you'll notice that last year we blew by 400 parts per million. We're on our way to 420 within another 2 or 3 years. That's carbon dioxide. Here's methane. This is the concentration of methane in the atmosphere by year. Notice that somewhere around 2002, 2004, here's 2006. Methane concentration in the atmosphere had sort of flattened out. But starting in 2006, what happened in 2006? Somebody answer. What started to happen in the U.S. in 2006? Yeah, shale gas development, shale oil development. 50,000 oil and shale gas and shale oil wells drilled in the U.S. since 2006. Is this a coincidence? The industry says yes. They say this is coming from cow farts or rice paddies. But the most recent paper published just last week has used modern detective methods, modern chemical methods, looking at isotopes of the various components of gases in the atmosphere. And that paper is the first to show very, very positive evidence that this is due to increased methane emissions from oil and gas operations in the United States. My country, this is global. This isn't methane concentration across the U.S. This is methane concentration in the atmosphere of our planet. So, geez, you know, the White House was really critical of us in 2011, but now here it is 2016, our Environmental Protection Agency is taking steps to cut methane emissions from oil and gas sources. Well, whoopee. Took them 5 years. And I'd be remiss if I didn't show you a picture of your premier and our president at a meeting earlier this year where they agreed that our two countries should curb methane emissions by undertaking regulations that would target oil and gas production. I haven't seen any evidence in your Yukon regulations of oil and gas production. I have not seen any evidence in those regulations that any extra effort is now being taken by regulation to curb methane emissions. Hasn't happened. Should. Finally, what does the science say about the negative impacts? Remember, the title of this talk is Negative Impacts, Bad Things. Don't take it from me. What does the science say? I'm only one scientist. I can't cover everything. What are the negative impacts on water, air, and human health, among other things? So an organization that I helped found back in 2010 is called PSE Healthy Energy. PSE stands for Physicians, Scientists, and Engineers for Healthy Energy. One of the most important things this organization has ever done, starting about 2 years ago, was to collect all of the known peer-reviewed literature. This is literature that's published in real journals. It's not bloggist shit. It's not somebody's opinion. It's not right-wing talk radio. It's not what you hear at a local bar. This is peer-reviewed literature published by bona fide scientists and engineers around the world. We've collected what we think is just about every paper that's ever been published in the area of shale and tight gas development. And we put them into a database online. Here it is. And it's very important for you in the Yukon, and you who are the regulators, I hope some of you are listening, the regulators in the Yukon, to understand that you now have one hell of an assignment from this professor. I like giving assignments. I'm a professor. I also like giving exams. So I hereby give an assignment to the regulatory authority of the Yukon that they have to read all 922 papers. But let's look at the history of those 922 papers. Here's a bar graph. In 2009, there were 6 papers. 6. Now, 2009 is 10 years after Texas started developing shale gas. It was 5 years after Pennsylvania and Ohio and West Virginia started developing shale gas. It was 5 years after British Columbia started developing shale gas. And nobody knew anything. There are only 6 papers in the entire literature. 6. The next year there were 6 more. Now there were 12. The next year there were 34 more. Now there are 46. The next year there were 73 more. And the next year 139 more. And the next year 201 more. And the next year after that, 256 more. So, I can tell you this. Over 50% of all of the knowledge that we have from these investigations reported in these peer-reviewed papers, over 50% of what we know, we've learned since 2014. Anything that happened before that was largely done in ignorance. Any regulations, provincial, territorial, state regulations, had to have been based on ignorance, because nobody knew anything. As of today, there are 922 publications in that database. To give you an example of the difference between a state that has been very, very careful and a province or a territory that perhaps is not being so careful, in 2008, my home state, New York State, declared a moratorium on fracking. Look, in 2008, there were only 6 papers. And yet New York State was wise enough, careful enough, and protective enough of its citizens to say, we don't know anything, so we shouldn't do it. As opposed to Pennsylvania that said, we don't know anything, let's do it. Ignorance is bliss. If you don't know that something is bad, go ahead and do it. Is that logical? The answer is no. But now, here you are in the Yukon, you're in moratorium for 1 more year. And so your regulatory authorities, your political leaders have to decide whether the Yukon is going to go ahead and develop shale gas. Excuse me, but here's the assignment. You better tell your regulators to go into this database and download all these 922 papers, because that is the body of literature on which the decision should be based. Not on opinion, not on politics, not on which side screams louder. Base it on science. So there's your assignment. There's your assignment. You make sure that your leaders, your political leaders, and your regulatory leaders know about this database. They cannot plead ignorance anymore. They can't say, well, we're not sure. Because let me tell you how sure we are. So this is what the database looks like. It's divided into 12 different categories. You pick: air quality, climate, community, ecology, economics, health, regulation, seismicity, waste fluids, water quality, water usage. We divided up all those 922 into these 12 categories so it's easier to figure out what you're going to do. Here's Avner Vengosh's paper. You heard from him not too long ago. But we published a paper this year in which we looked at 3 particular topics: air quality, water quality, and human health. And we read every paper in each of those 3 topics. And then we categorized the paper as to whether the paper said, this is really bad, or we can't tell whether it's bad. And let me tell you what we found. Human health impacts. We found that 87% of the papers directly addressing human health impacts found bad human health impacts. 13% of the papers didn't find any bad human health aspects. But no paper said people are healthier because of shale gas than they were before shale gas. Nearly 9 out of 10 papers say bad things will happen. Bad things have happened. Bad things will continue to happen. Air quality, which of course is related to human health. 92% of the papers in the category of air quality found bad impacts, negative impacts on air quality. No paper published to date has said that the air quality near shale gas development is better than it was before shale gas development. That's impossible. Over 9 out of 10 say it's worse. Water quality. Nearly 3/4 of the papers have concluded that there has been water contamination due to nearby shale gas or shale oil development. What we're trying to figure out here is consensus. That's the way science works. You get a large number of scientists over a large area, geographical area, the US, Canada, Europe, and you look at the big picture, all the possible things that can happen. And you study those things over a long period of time, and then you publish. And you get reviewed, and you get criticized, and you hone in on the truth. And eventually, science always reaches a consensus, a yes or a no. In the meantime, there might be a maybe, there might be a probability, but eventually the probabilities become so significant that something is true that science declares it to be significant. Consensus has been achieved. I'm not going to sit here tonight and tell you that there is universal consensus yet. This is still only 922 papers. And many of these papers are the result of what are called longitudinal studies. They take years and years. If you're going to study health effects due to radiation or health effects due to ingestion of particulate matter, you can be causing health effects that don't appear for many years in the human. So you have to study a large number of human beings over a long period of time in order to make conclusive evidence, to get conclusive evidence that a health effect is actually true. So we're still at the beginning, but the problem is we didn't start until 2014. And there had already been 25 or 30,000 shale gas and oil wells in the U.S. So we might have already harmed people. The probability at this point is that we have harmed people before we knew any better. So let me summarize because I'm at exactly 1 hour. So because of spatial intensity, you know what spatial intensity is now, a hell of a lot of wells, a lot of pads in an area, and technologies of scale, shale gas and oil development requires everything to be bigger. Here's what's going to happen. The risk of groundwater contamination are very high. Not because of fracking, but because of wellbore integrity, loss of wellbore integrity, leaking wells, surface spills, and waste disposal. Those are the key issues for groundwater contamination. The impacts upon your landscape, I showed you what a pad looks like, and I showed you how close those pads are. It will be considerable and it will be permanent. The effectiveness of existing legislation and regulation. I have read the Yukon regs. They are poor. The word shale does not appear in your regulations. The word unconventional does not appear in your regulations. Your regulations have not been updated to account for modern development of oil and gas from shale formations. They're essentially the same regulations that were written for conventional oil or gas many years ago, and they have not been updated. I'm pausing for effect here. Our state of Maryland, which only has a relatively small amount of shale gas and no oil at all, it's just shale gas. Only a very small percentage of our state of Maryland has it, just passed their modern regulations. And they are the toughest regulations on the face of the earth. If you want to see what tough regs are, go read the new regs published by the state of Maryland. For example, how close can a company drill a shale gas well to a private home in Maryland? 600 meters. 2,000 feet. I'd be willing to bet that there is nobody in the oil and gas industry who wants to operate in the Yukon who would accept that. They would say, that's too far. That would take so much land out of possible use, it wouldn't be economical for us to develop. Well, good. But it would be protective of your water and protective of your air. 600 meters. How about the potential net economic outcomes to the Yukon and the rest of your country? I don't know if you noticed this, but the U.S. shale gas and oil have gone bust. Of all the shale gas plays in the United States, only one is still increasing its production. All the rest of them are in terminal decline. All the easy-to-get stuff has already been gotten. So, no, I can't imagine any company with any brains who would walk into the Yukon now and try to develop shale gas or shale oil with the prices that are existing. But as the prices go up, which they will eventually, some company's going to come in and say, let's try it. And you better be ready, hopefully, to say no. Because you're not going to get anything out of it. You're going to get all the pain and none of the pleasure. And finally, you know, because you're in a northern climate, You know that climate change is real. Global warming is occurring much faster in the northern climes than any place else on the face of the earth. You know that. You're experiencing it. Donald Trump wouldn't believe it, but you should. So you would be adding additional carbon dioxide and methane to the atmosphere if you allow this to happen in the Yukon at a time when we should be decreasing, not increasing, both greenhouse gases. The Yukon has to make a moral decision. You all have read enough to know that of all the oil and gas and coal still underground, 80% of it has to stay there. Of all the oil and gas and coal still underground, 80% of it has to stay there if we're going to try to make sure that global temperatures don't reach 1.5 degrees centigrade above the norm. That means that every region, every state, every province, every territory has to decide what part of our resources are we going to keep underground. New York has already made its decision. There will be no shale gas development in New York. New York has voluntarily said, we're going to keep ours underground forever. I would suggest to you that you should suggest to your leaders that given where you are in the Yukon, given the tremendous effort it's going to take, the tremendous amount of capital it's going to take, the tremendous difficulties it's going to ensue for the companies and for you, that it's ludicrous, stupid and ludicrous to begin to develop shale gas and oil in the Yukon. A few people will benefit, obviously a few politicians, a few oil and gas magnates, but the people of the Yukon, So let me conclude there. I want to thank you all for allowing me to meet